using maps to build fractals. But before getting into this topic, let's consider a slightly different story. So what I want to do first, I want to describe counter set. So it's quite useful to have this kind of description of counter set, more arithmetical rather. So let me remind what is counter set. We at step 0 we have a segment from 0 to 1. At step 1, let's correct it. So we will consider as all numbers from 0 to 1, so excluding 1. At step 1, we divide this segment into 3 pieces, and we will remove middle third, and we will have 2 segments with one side open. This will be from 0 to 1/3, and this from 2/3 to 1. And at step 2, each of these 2 segments divided into 3 pieces. And we also we get new 2 segments from each of them. And here will be from 0 to 1/9, here from 2/9 to 3/9, or 1/3. Here from 6/9 to 7/9. And here from 8/9 to say 1, and so on. Let's try to describe numbers which are inside of this segment. For example, for this one, we have a number, it's a fractional number, 0.A1, A2, and so on, AN, and so on. Here would be good now to have a description of this set. Would be good to use base 3 system. We will use base 3 system, counting system, and therefore AI is one of these digits. It is 0, 1, and 2. We don't have digits 3 and above. Now let's consider what happens at step 1. So at step 0, this A1, A2, and so on, AN, any numbers. So AI is any digit from 0 to 1, 0, 1, and 2. Now at step 1, what says step 1? Step 1 says that we get rid of a segment in the middle. And here segments in the middle are, in fact, are all numbers with A1 equal to 1. So what it means? It means that step 1, we removed all points with coordinate having digit digit 1 at first position. So A1 now is not equal to 1. So what we have here? Here A1 is 0. Here A1 is 2, but A1 equal to 1 is removed. So all numbers which have 1 at first position here, they are removed after first step. If we consider step 2, we will see that all numbers with A2 equal to 1 are removed. So A2 now is not equal to 1. In segments, in numbers, so in points in remaining segments, and so on. Then we can climb. No, we don't need to. So step n. An is not equal to 1. So what we got? We got description of counter set. Which is all numbers such that AI is not equal to 1 for any I in base 3 system. So we can say it's all set of all numbers, or we can say it is set of all points such that their coordinates don't have digit 1. Now let's consider how we can use maps to build counter sets. Using maps, to build counter set. So I will illustrate it in 2 different ways. First way, let's consider map. Xn plus 1 equals to 3xn if xn is between 0 and third. 0 if xn is between third and 2/3. And 3xn minus 2 if xn is between 2/3 and 1. So what we have? So this is our map. So it's xn plus 1. So 1, say here 1. So first branch is stretching 3 times of all this segment from 0 to 1/3. And there is one more branch, which is stretching segment from 2/3 to 1. Two-thirds. So what we see, xn plus 1 is not equal to 0 if xn belongs to 2 segments from step 1 in building counter set. So here, okay. Again, so this may be here and here. So if xn between 0 and 1/3 and between 2/3 and 1, then xn plus 1 is not equal to 1. So we can, in fact, what we can say, it's the same map, just it is the same map. Can be presented as, we already seen it, I have already shown it before, xn plus 1 equals to, let's say, 3xn mod 1 if xn between 0 and 1/3, or xn is between 2/3 and 1, and 0 otherwise. It is the same map. Now, what happens next? Let's consider second composite of x. Second composite of x like this. I will put it. So this is, let's say this is x naught. This is x2. 0 reaching 3 squared times. Therefore, we will get to 1 when x equals to 1/9. Then this piece will be missing again now. And again, stretching 9 times. From 2 9s to 3 9. To explain, I will slightly change here notations. I will say this is xn plus 2 and here xn plus 1. Now what we see that xn plus 2 is 3 times xn plus 1, provided that xn plus 1 between 0 and 3rd and between 2/3 and 1. Otherwise it's 0. If we get here, we will see this is, say, 1/3, this is 2/3. So xn plus 1 is between 0 and 1/3 if xn is between 0 and 1/9. And it is between 2/3 and 1 if xn is between 2 9s and 3 9s. This is 2 9s. And same is here. It is between 6/9 and 7/9 here, and between 8/9 and 9/9 here. So this. And therefore, we get f2 is 3 times xn plus 1 or 9 times xn on when xn is between 0 and 1/9. And well, x naught is between 0 and 1/9, or between 2/9 and 3/9. And here it was the same. So it is 3/9. Let's put it like this. Here say 2/3, and here say 1. And this will be the same. So it will be sharp and sharp. So here we will have 7/9, and here we will have 8/9. So what we got x2 is non-zero if x naught is here, 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 and here. And this is exactly x2 is non-zero when x naught is inside the segments. from step 2 in building counter set. Then Fn of x not 0 when n tends to counter set. So this is statement we can make. There is another way to build counter set using maps. It is about combining maps. Again, let's build counter set different way. So we have again, this is 0, 1. It is our original segment. This is step node. Then we have 2 segments. Step 1. And so on. I will consider only these 2 steps for now. So at step node, this X node belongs to the segment 0, 1. At step 1, we have X1, which belongs to 0, 1/3, and 2/3, 1. How we can build this kind of X1? We can build X1 in applying maps or applying 2 different maps. So first map, let's say first map, we'll call it omega 1. So it is like this, X1 equals to 1/3 X naught. First segment. And second map, omega 2, X1 equals to 1/3 X naught plus 2/3. So it is again. So this what it does. It's here we have shrinking. So this shrinks segment 0, 1 to segment 0, 1/3. Here we have also shrinking, but also shift. So this is shrink. And this is shift. And therefore our map will be like this. Step 1, we will apply maps twice. Apply map omega 1 and apply map omega 2. And you will do it the same. So at any step, so we can say step n, apply 2 maps. And this way we get counter set again. Counter set. This is particular case of counter set, which is middle third. And finally, I will show how to use maps to build core curve. This is interesting case because here we will encounter two-dimensional maps for the first time, and we will talk about two-dimensional maps from the next lecture onward. Let's consider Koch curve again. At step node, we have segment from 0 to 1. At step 1, we divide it into 3 pieces, and middle third is replaced by 2 segments of the same size, so 0, 1 over 3, 2 over 3, 1. And in addition, we add two extra segments. So what is important here? Koch curve is two-dimensional structure. Two-dimensional. Maybe not two-dimensional. Maybe it will be two. Let's say is planar. You need plane to build it. And since it's planar now, what we want to do, we want to introduce two-dimensional maps. So this xn plus 1, yn plus 1, now it will be point on the plane, which equals to some kind of function. Well, we can put it f of x and yn. Well, let's put it like this. f1 x and yn, f2 x and yn. So this is 2 dimensions, but we will consider linear maps. We can use linear maps only, at least for this particular case, linear maps. Therefore, xn plus 1, yn plus 1 can be represented as some matrix, 2 by 2 matrix times xn yn plus vector p. Let's say p1, p2. This is linear map, two-dimensional linear map. Now, transition. So if we consider first map, it is this one. Let's say this is first segment, second segment, third, and fourth. Therefore, we will need to combine 4 maps. First map is relatively easy. Segment 1. So segment 0, 1 is just shrinked to segment 1 over 3. So segment 1 and any other segment generally can be, so shrink of segment. Shrink and keep position. Xn plus 1. Yn plus 1, shrinking is relatively easy. Yeah, for into two-dimensional case. It is 1/3. And if we will put here identity matrix 1, 0, 0, 1, x, n, y, n. So what we get here? Here, any segment starting at the origin is shrinked 3 times and with left orientation. Shrinked 3 times. Orientation is kept. is not altered. So this is our first map. Let's put it like this. Omega 1. So our first map is xn plus 1 by n plus 1, shrinking 3 times, keeping orientation xn by n. If we want to consider second segment, the second segment is a bit more difficult because we indeed shrink, it's fine, we have this shrinkage, but in addition to shrinkage, we have rotation and we also have a shift. So shift by 1/3, okay, let's put it like this, building omega 2. Shift is easy. Shift is xn plus 1 by n plus 1. Shrinkage also is it's 1/3. Rotation, some kind of matrix A, xn by n plus, so it is shift along x coordinate, so this is x coordinate, this is y. So it is shift along x coordinate by 1/3, so this would be no shift along vertical and shift by 1/3 along horizontal. So this is shift, this is shrinkage, and A to be found, A change in rotation. This is to be found. Now what happens? Rotation is, so it is rotated by 60 degrees. Yeah, this is equilateral triangle. This is pi/3. To find E, let's consider rotation of segment on the plane. Let's consider plane xy. Let's consider segment of length 1, say under angle alpha to x coordinate. Assume we want to shift it, to rotate it, sorry, by pi/3. Then this point, which has coordinates, let's say x0, y0, will have coordinates x1, y1. So this is original point and this is its image. So we only rotate, we don't change distance to the origin. Then x0 equals to cosine alpha, y0 equals to sine alpha. Yeah, this is cosine and this is sine. And if we check now with x1 and y1, x1 will be again cosine of all this angle, which is alpha plus pi/3. And this, using trigonometric identities, it will be cosine alpha times cosine pi/3 minus sine alpha times sine pi/3. And this cosine alpha is x0 times cosine pi/3 minus y0 times sine pi/3. And similarly, y1, which is equal to sine alpha plus pi/3, can be represented, again, we will use trigonometric identity for sine of sum of angles. It is sine alpha times cosine pi over 3 plus cosine alpha times sine pi over 3, and this will be equal to y naught times cosine pi over 3 plus x naught times sine pi over 3. And if we put this all together, we will find following representation for x1, y1. x1, y1 will be equal to, you can check it, cosine pi over 3 minus sine pi over 3 sine pi over 3 cosine pi over 3 times x naught, y naught. And this is our A. So A rotates segments by pi over 3. And therefore, and therefore our map omega 2 is given like this: xn plus 1 yn plus 1 equals to 1/3 this matrix which we found, cosine pi over 3 minus sine pi over 3 sine pi over 3 cosine pi over 3 x n yn and plus 0 and here 1/3. We found it before. This can be represented a bit differently. We can put it like this: 1 and here 1/3. So this is this map to build segment 2, and you can similarly find yourself. Omega 3 is 1/3, so it should be same shrinkage. And now here we will find out that rotation should be by 2 pi over 3. Just check it. Look at Koch curve until you find out that rotation by 2 pi over 3. Therefore here will be cosine 2 pi over 3 minus sine 2 pi over 3 sine 2 pi over 3 cosine 2 pi over 3. And now shift by 2 pi 1 0, and this is, I would suggest you to check why this is. Okay, so this is x, it's shift along x, and therefore here was wrong. Here should be 0, and here should be 1. So we shift along x direction. This is shift along x-axis, and here also along x-axis. So first coordinate x and second coordinate y. And last segment is relatively easy, where it was. So this is segment number 4, it is shrinkage by, it's shrinkage 3 times shrinkage, and shift along x-axis by 2/3. So this is relatively easy. Omega 4 is xn plus 1 yn plus 1. So 1/3 identity matrix, no rotation, xn yn plus 2/3 1, 0. And therefore, step n, now we can say step n is applying omega 1, omega 2, omega 3, omega 4. This way you will get at step n core curve, and then you will apply this again and again, and this way you produce core curve. Okay, goodbye.